All right, subscribers, welcome back to another episode of Science with Surback. Today what we're going to be talking about is section 17.2, which deals with the topic of current in electricity. So before we get going into notes, there's a couple of objectives that you should be able to accomplish by the end of this video. Objective number 1, determine how electrical potential energy and gravitational potential energy are similar. And objective number 2, determine the cause of electrical resistance. So we start out here with what is electrical potential energy. And electrical potential energy is defined as the ability to move an electric charge from one point to another. Now, this movement is dependent upon an electric charge in an electric field. So when we talk about potential energy, we are going to be discussing the movement of negative charges. And what we have to keep in mind when we're talking about the movement of negative charges is this. The negative charges, are going to move away from another negative charge. And this movement is a result of the first negative charge of an electric field. So now that we understand the movement of current and specifically the movement of negative charges, what we can do is we can talk about changes in electrical potential energy. So we have to know that the electrical potential energy is going to decrease when a charge repels another charge, and this is because the electric field of one charge does work on the other charge. Now, the potential energy is going to increase when a force pushes a charge in the opposite direction of the electrical force. Now, something else to note about the electrical potential energy is this. This is the distance's effect on potential energy. Now, I'm out of room, so I'm going to grab another sheet of paper here, and we're going to talk about the distances. So again, this was supposed to go on the other sheet of paper. I ran out of room. But the two things that we need to talk about, or the first thing, is this, the repulsive forces. And these repulsive forces are electrical potential energy increasing as charges move closer to each other. And the other thing that we need to discuss here is attractive forces. And this results in electrical potential energy decreasing as charges move closer to each other. Okay, so now what we can talk about is the potential difference. So we've talked about potential energy, and we move to another concept we know as potential difference. Okay, so the potential difference is defined as the voltage difference between 2 points in a circuit. Now, to put it in another perspective here, the potential difference is equal to the change of electrical potential energy of a charged particle divided by that plus or minus charge. Again, so here is this same definition in a mathematical formula. The potential difference is the change of electrical potential energy of a charged particle all divided by that charge, which can either be positive or negative. Now, this is going to occur when a charge moves from one place to another in an electrical field. So while we're talking about the potential difference, the SI unit for the potential difference is the volt. Now, 1 volt is equal to 1 joule per coulomb. So we're tying a lot of concepts together here with our concept of the volt. A joule, remember from previous chapters, was a unit we utilized to express energy. And that coulomb we just learned in section 1 of this chapter was a way to express charge. Okay, so it's energy per charge is what we're thinking about here with the volt. Now, Voltage is the term often used to describe potential energy. So with this knowledge of potential energy and potential difference in mind, we can now move on to some different concepts here. And those concepts are, or we'll start with the concept of an electrochemical cell. Okay, so an electrochemical cell is defined as a group of connected cells that convert chemical energy into electrical energy. Now, as we talk about this here, we need to talk about this term known as the cell that we describe this electrochemical business with. So a cell in this case, what we're talking about here, is a device that produces an electric current by converting chemical or radiant energy into electrical energy. Now, let's put this in perspective and go over an example. And so for this example, I am going to draw a few things that we can identify in our electrochemical cell. So I'm going to start out this with a beaker here. And right next to it, I'm going to draw another beaker, okay? And so within these two beakers, what I'm going to have are two pieces of metal. And this piece of metal here on my left-hand side is going to be zinc. So I'm going to label that as the chemical symbol of Zn, and so that is zinc metal. And then over here, I'm going to make another rectangle piece of metal, and this piece of metal is going to be copper. So I'll label that as the symbol for copper, and then I'm going to connect these with a wire, okay? And so in this wire, we're going to show the flow of electrons. Now, within these beakers, if you can imagine here, I poured in a solution of zinc sulfate. So this is a solution of zinc sulfate, and kind of some interesting things happen. When I put zinc sulfate in solution, we get zinc ions, which are Zn2+ ions, and SO4 2- ions. Again, this is a solution of zinc sulfate here, and that produces those particular ions. Now, in this solution here, I have a solution of copper 2 sulfate. So again, when you put copper 2 sulfate in a solution, you get copper 2+ ions and SO4 2- ions. Now, how we connect these two solutions together is through a salt bridge, okay? So a salt bridge, in this case here, I'm going to draw it in purple. A salt bridge would look like this. It would dip into and have an opening. It dip into one of the beakers and come over and have an opening and dip into the other. And this would connect these two solutions, the zinc sulfate and the copper 2 sulfate, together. Okay? Now, within this, again, we call this a salt bridge because we need the transfer of some chemicals, or we need the transfer of some ions to help make our electricity roll. So this salt bridge here would have 2 sodium ions and an SO4 2- ion. And all this does is it allows the ions to exchange with, or what happens here as a result is it allows the transfer of an electron to go from the zinc to the copper, or the anode to the cathode. So I just want to put one more thing here. This right here that I'm writing down in red is the direction of travel of these electrons. So the electrons would go from the zinc to the copper metal. And it's all because it's connected in this sort of setup. Now, what I also want to talk about here is the exact definition, so you have an idea of what I just explained here. So, number one, we need to talk about this electrolyte solution. So I'm going to highlight this here in green. And so the electrolyte solution is in each of these beakers here. And so the electrolyte solution is a solution that conducts electricity by producing ions in solution. Okay, so some other things contained within our electrochemical cell are these electrodes. And I'm going to draw arrows here. The electrodes are the actual metal strips here that allow our electrochemical cell to function. So again, these metal strips here, the zinc and the copper strips, these are known as the electrodes. Okay, so within electrodes, there's two different types. Number one, the type that I want to talk about first, and I'm going to write this in red, is the anode. And the anode is the electrode that releases the negative charge. So because zinc is releasing this electron or the negative charge, it, in this case here, is what we call the anode. So again, I'm going to pause. I'm going to write the definition of this anode in our example. And the other electrode here on the other side that accepts the electrons is going to be known as the cathode. And that's because it accepts those negative charges. Again, the cathode says this is the electrode that accepts the negative charges, which we call negative charges are electrons in this case here. Okay, so now we have an idea of how this operates, and we can take a little bit closer look at the electrochemical cell that is occurring within a battery. So to help describe this electrochemical cell of a battery, I have this picture that I am going to reference here. So notice the couple different things that we have and the couple things that we're going to discuss. I'm going to put this right where we can see it, and I'll shift it and adjust it as we go through this part here. So number one, we have to remember that this battery is going to contain two terminals. And so as you can see from the picture here, the one terminal is a positive terminal and the other terminal is a negative terminal. Now within the battery, the positive terminal is the cathode, or the portion that accepts the electron. And the negative terminal is the anode, or the portion that releases those electrons. So now, from our last picture that we just talked about there, we had what we called an electrolyte solution. And so the electrolyte solution, or the electrolyte area in which the positive and negative ions are contained, are a little bit different here in our battery. So I'm going to write that down and make our starting note here when we talk about our electrolyte area. So the first thing that I want you to identify is this. The electrolyte area, just like we saw on our last picture, is the area in which the positive and negative ions are contained within our batteries. And I want you to notice here that we have two different electrolyte areas, and I want to talk about each of these electrolyte areas. Okay, so we have, again, two different electrolyte areas that we need to talk about. The first one is a wet electrolyte. And the wet electrolyte is where the ions are contained in a solution. And this wet electrolyte is something that's seen in a lead acid battery or the battery of a car. So I want you to note that is that seen in the battery of a car. And in the case of a car battery, that wet electrolyte is a solution of sulfuric acid. Now, what we have here in our picture is something known as a dry electrolyte. And in a dry electrolyte, ions are contained on a paste-like material. Now, a dry electrolyte is a common type of electrolyte that's seen in our common everyday batteries, such as a AA or AAA or C type of battery. So again, depending on the type of battery will determine what type of electrolyte we have. Okay, so now we need to talk about here what is going on in our battery to power this flashlight in our example. So we need to keep in mind that as electrons flow from the negative terminal, okay, so the negative terminal to the positive terminal, it's going to allow power to be harnessed from the battery. Now, before I pause and write that down, remember, we have our negative terminal that is producing the electrons, and it, if you can see here, is connected to the electrode that is allowing the flow of electrons to happen and go to the other electrode, the cathode, and release those electrons. Okay, so I really want to piece this all together and talk about the battery and how we can get the flow of electrons to actually power the flashlight. So what I'm going to do is I'm going to grab another sheet of paper and we're going to go over the exact use of batteries in a flashlight in terms of an electrochemical cell. Okay, so I'll change papers here. And what we're going to discuss here is, again, we're going to utilize this picture and we are going to discuss the uses of batteries in a flashlight. So when you turn on a flashlight, the terminals of the battery are connected by the bulb of the flashlight. Now, when the flashlight is turned on, it's going to create a voltage across the filament of the light bulb. And remember, the voltage is the term we associate to describe potential energy, so that flow of that potential energy. Now, when we have this voltage across the filament, it's going to cause a potential energy difference. And this potential energy difference causes the charges within the battery to move from an area of higher potential energy to an area of lower potential energy. Now, this charges here, as they move from area of high to low in terms of potential energy, it's going to cause electrons to flow through the battery and allow the light bulb to be lit. Okay, so now we have an understanding of how our typical everyday batteries that we encounter work and how they can be used to power something as simple as a flashlight. What we are going to move on to next is talking about this electrical current. So electric current is defined as the rate at which charges pass through a given point. And the SI unit for current is the ampere, or just a big capital A. Now 1 ampere, 1 amp, is equal to 1 coulomb of charge moving past a point in 1 second. Now what we can also talk about with electric current is a concept known as direct current. And direct current is current in which the charges always move from one terminal to another in the same direction. Now, direct current can be made up of positive charges, negative charges, or a combination of both positive and negative charges. And a good example of direct current is in a battery. Now, what we call direct current here, you may have commonly seen this as DC power. Another concept here, as we're talking about current, is what we call conventional current. Now, you may hear conventional current referred to as AC power. Okay, so these are two common terms here. But in conventional current, the current that moves in the opposite direction, the current moves in the opposite directions that the electrons move. Now, conventional current is made of positive charges that are going to have the same effect as the actual motion of the charge in the material. And so to sum this all up, the direction of current in this conventional current is opposite to the direction that the electrons move. Okay, so this allows us to talk about the concept of electrical resistance. And electrical resistance is defined as the opposition presented to the current by a material or a device. Now, this can be caused by internal friction, which slows the movement of charges through a conducting material. Now, resistance can be measured through a relationship between the voltage across a conductor and the current running through it. Now, resistance is measured in this way because internal friction is difficult to directly measure. Now, let's take this into an example of something we may have seen on an everyday basis here. Okay, so our example is going to be a 100-watt light bulb versus a 40-watt light bulb. And what I want you to know is this: those light bulbs that we plug in here to our outlets here in the United States, they're designed to receive the same voltage of 120 volts. Now, the 40-watt light bulb is dimmer, okay? So 40-watt light bulb is dimmer. And the 100-watt light bulb is brighter. And the reason for this difference is that the 40-watt light bulb has higher resistance and the 100-watt light bulb has less resistance. So by stopping that flow of electrons, it's going to, in this case, show that we have a less bright light compared to one that lets the electricity flow and has lower resistance and causes a brighter light bulb. Okay, so now we can move on and start talking about the specifics about resistance. And these specifics are related to the mathematical concepts. And so we get into the topic of Ohm's law. Now, Ohm's law is going to relate the concept of resistance, and it's going to state that the resistance within electrical conductors indicates how much the motion of charges within its resisted within it is resisted because of collisions. Now, what we have to keep in mind with this statement that I just wrote here is that as electrons are moving through a conductor, some of those electrons will collide with atoms of that material of the conductor. Now, these collisions cause kinetic energy of or as the electron is transferred to the atoms. Now, this transfer of kinetic energy causes atoms within that particular conductor to vibrate and heat up. Okay, so with Ohm's law, we do have a formula that is associated with it. And this formula I'm going to write two different ways. One is the resistance. The resistance is equal to the voltage divided by the current, or we can use simple symbols here where R equals V over I. Now, it's important to remember this. If you're going to use these symbols, the R is going to stand for resistance, and resistance is going to be in the unit of ohms, okay? So an ohm kind of looks like a horseshoe here, and that is the unit for resistance. Again, this symbol right here for resistance is called the ohm, and 1 ohm is equal to 1 volt per amp, or how we have it written here. Now remember, 1 volt could be 1 V over capital, that should be a capital A for amp. Now, our V stands for volts. Okay, so our V stands for volts, and then our I is going to stand for our current, which is going to be in units of amps. All right, so remember this formula. We're going to use it here now in an example. Okay, so we're going to use Ohm's law, the thing that we just went over to go through this example. We have the headlights of a typical car are powered by a 12-volt battery that's underneath your hood. We want to know what is the resistance of the headlights if they draw 3 amps of current when they are turned on. Okay, so remember our formula for Ohm's law is the resistance is equal to our volts divided by our current. So our resistance here is something we don't know. It did not give us ohms, so we have to go find our resistance. Now our V is just the voltage that the headlights are being provided, and so the voltage that they're being provided is 12 volts. And then the current, which we use the symbol of I, is in amps, which is 3.0 amps. Now, to find the resistance, all we need to do here is we need to take R equals our volts 12 divided by our I for amps. Okay, so we're going to take out our calculator here, and we are going to take 12 divided by 3. And we get a value of 4. Now, this can be expressed in two ways: volts per amp, or for ohms, which uses this symbol that looks like a horseshoe. Either way is correct, but we need to make sure we have those units expressed. Now, with our business talking about Ohm's law, we can have this business talking about resistors. Now, resistors, I want you to write this down. Resistors are a special type of conductor used to control current. So now what I want to do is I want to bring up some concepts we talked about in section 1, and that is conductors and insulators, and relate it to this business of resistance. Okay, so conductors, remember this. Conductors allow electrons to flow easily and cause a high current. Now, there is little resistance that is experienced through conductors. Now, it's important to keep in mind that good conductors allow electrons to flow easily under the influence of an electric field. And an example of good conductors are metals, because electrons can move freely through them. So let's take an example here and go back to turning on a flashlight and how we can relate it to conductors in the business of the resistance within a conductor. So when you turn a flashlight on, the light seems to come on immediately. So what's specifically happening is that when a voltage source is connected to the conductor, like the flashlight, the electric field is directed through the conductor at almost the speed of light. And so that is why when we turn that flashlight on, it almost instantly turns that light bulb within the flashlight on. Okay, so we've talked about conductors and resistance. Now we're going to shift gears and talk about insulators and resistance. So remember, insulators are going to have a high resistance to charge movement. And this is used to prevent electric current from flowing in directions other than the desired direction. And so a good example of this would be the plastic coating around the copper wire of an electric cord. And so again, if we bring out the cord here, the plastic part here, this is going to keep the current from escaping into the floor or into your body. Now, another topic or another concept that we can discuss with insulators is that of a ground wire. Now, a ground wire is a wire in an electrical socket that is connected to the ground. And what this does is it conducts any excess charge to Earth, where once in Earth it can spread over the planet safely. Now, some other terms and concepts that we can talk about here is the concept of a semiconductor. So semiconductors have electrical properties of both insulators and conductors. And in their pure state, they are insulators. But when impurities are added to semiconductors, it greatly increases the semiconductor's ability to conduct electric charge. And so some examples of semiconductors include things or elements such as silicon and germanium. And these are often things used in electronics. And so you may have heard the term coined Silicon Valley, and that's an area in California where a lot of the computer development occurs. And the reason they call it Silicon Valley is those computers are using quite a bit of silicon to process things correctly, and that's where that name Silicon Valley is coined from. Okay, so our last thing that we need to talk about here is superconductors. And superconductors are materials that have zero resistance when their temperature falls below a critical temperature. Now, when we're talking about this, we need to talk about this concept of a critical temperature. And the critical temperature is going to be unique for each material. But this critical temperature can range from negative 272 degrees Celsius to as high as 123 degrees below zero for Celsius as well. So I want you to notice that these are both negative and they're pretty low temperatures here for a superconductor to go through this process. Now, with a superconductor, if a current is established in a superconductor, it will continue even if the applied voltage is removed. And in fact, for superconductors that have been established in the lab, they made these loops that have been observed to continue for many years. Now, you may be wondering, okay, well, that's great if we can make this substance really cold and apply some voltage and remove it and have that current continue, but what's our application that we have for this? And one application is used for superconducting magnets, which can levitate our commuter trains. And so with these superconducting magnets here on commuter trains, and this is something that has been done here, what that does is that allows little to no power to be required to operate the trains. So if we can better utilize and better cool these materials to be superconductors, we can have a lot of good power applications that we could utilize this for. All right, so hope you have enjoyed this episode. We took a deeper look into the concept of electricity. And as always, if you haven't already, make sure you subscribe.